Welcome to this presentation wherein we will derive the Z transform transfer function. We will start with the model of the magnetically suspended ball system. We will obtain the transfer function and discretize it. We will also obtain performance specifications. Recall the problem statement. We discussed this in the first part of this course. We have current through the coil introducing magnetic force, and that balances the force due to gravity, and hence this ball is suspended in mid-air, and we may want to move this to another position. Here are the equations that we considered. We have force balance and voltage balance, and we stated that in matrix form with the following deviation variables, and then we assigned values for various parameters. With this we obtained this state space equation. Recall this x1 denotes the position in deviation variable, and that is the only variable we propose to measure. As a result, if I write y as Cx, C will be equal to 1 0 0. This 1 will correspond to x1, which is the position variable. When I take transfer function in Laplace domain, I get the following transfer function g of s given by this. Later on I will give a Scilab code wherein all of these will be calculated, and you could go through each step and verify that you get all these values. Let us sample this continuous time model using a sampling time of 0.01 second. Using the function that I have written called myc2d.sci, you get this transfer function, which can be simplified like this, wherein I have written everything in powers of z inverse. So numerator is a polynomial in z inverse, so is the denominator, and that is defined as z power minus k into b by a. We will always use b to denote the numerator and a to denote the denominator. So this is the expression we had in the previous slide. Now split a and b into good and bad parts. Let us first do this for the denominator a. A is ag into ab, and the second and third factors have their zeros inside the unit circle, so I call it ag. The rest of it is the bad portion, I call it ab. Similarly, do this for b. This has a 0 at minus 0.2033, which is inside the unit circle, so I call it good portion. I have kept the constant also, the gain also along with this. The rest of it is the bad portion. The 0 of this factor is outside the unit circle. We also have k equals 1. Remember, z power minus k is equal to 1. Now we go on to specifications. We demand small fall time in error. Remember, we considered this in the first part of this course. As a matter of fact, this entire slide is reproduced from one of the lectures I delivered in the first part of this course. Start with this error signal. Error becomes 0, that is En equals 0 when omega n equals pi by 2 the first time. Of course, it can happen 0 for some other future values of n also, but this is the first occurrence wherein En equals 0. This expression we solve for n. We want this n to be less than some nr, a user specified value. So we get pi by 2 omega less than nr, or omega greater than pi by 2 nr. We diagrammatically showed this as follows as a shaded region as given here. The next specification is that we want a small undershoot. So when does En equals rho n cos omega n reach the first minimum? We may be tempted to differentiate and equate to 0, but this is not applicable because n is an integer. So we look for a simpler approximate expression. It reaches minimum when omega n equals pi, or when I substitute omega n equals pi in this expression, I get this, which can be simplified as minus rho n, and when I substitute for omega n, I get this expression. This is the minimum, whereas the user specified maximum deviation is epsilon. So as a result, we get the absolute value of this to be less than epsilon, which can be written as rho less than epsilon to the power omega by pi, and we got this diagrammatically as given here. So let us summarize the problem statement. We want to control this plant g of z obtained by sampling a continuous plant with Ts equals 0.01 s, and the transient specifications for a step input are now given by the user. We want the steady state error to be less than or equal to 2%. Of course, this is automatically satisfied by the choice of our error model. We are told now that the overshoot epsilon is less than or equal to 5%. Settling time is less than or equal to 50 seconds. The rise time unfortunately is not specified, so we will make a guess. We will guess it to be about 1/3 of the settling time. So we guess it to be about 0.15 seconds. Now with that, we will determine our polynomial phi CL. The rise time condition becomes n equals rise time by Ts. This was 0.15 divided by 0.01, that is 15, and omega is chosen as pi by 2n. So let us substitute for n as 15. So we get this omega to be 0.1047. The next one is the overshoot constraint. We have rho to be less than this expression and epsilon is 0.05. So let us substitute for omega and pi also here, simplify it, we get 0.905. We will choose rho to be equal to 0.905, and the desired closed loop poles are at rho into exponential plus minus j omega. We obtain the expression for the desired closed loop characteristic polynomial as given here. We can simplify it, substitute values, we get this expression. So we arrive at the specification, we arrive at the phi that we want. Now we know all the things required to design the controller, which we will do in the next video. Thanks for joining. Goodbye.